All right, so today I want us to talk about complex numbers for the first third of the class or so. And then we're going to review sinusoids a little bit just to kind of get ahead of the game for what's going on with what we're starting next week. So let's see here. Does anybody know what a complex number is? Let's start there.
Either I or no. We take the square root of a negative.
So when we take the square root of a negative number, that's an imaginary number. Matthew, you had your hand raised a moment ago. Exactly right. So Trevor, you were half right. Matthew was fully right. A complex number is a number that has both a real part and an imaginary part. Okay. So I'm going to draw a complex plane in the middle of my page here. Okay. And so I want you guys to think about this as two number lines that are 90 degrees, like they're orthogonal to each other, I guess. So we're going to put our real numbers on the horizontal axis, and we're going to put our imaginary numbers on the vertical axis. So this is literally just the number lines like you guys learned about in, I don't know, first or second grade or whatever. And then we're putting another one and we're just rotating it 90 degrees. Okay. So whenever we're talking about complex numbers, we can represent them in several different ways. Okay. So the first way that we could represent a complex number is what's called the rectangular form. So in rectangular form, we might represent a complex number as follows. So I'm going to say that I have some complex number, capital A, and I'm going to put a bar over it. And that's what's going to let you guys know that I'm dealing with a complex number. In your textbooks and stuff like that, you might see these typed as boldface letters, but I can't write in bold. So I put a bar over the top to let you know what's going on. And I'm going to write this as lowercase a plus JB, where the real part of complex number A is that lowercase a, and the imaginary part of complex number A is that lowercase b. So for what it's worth, J is simply the square root of -1. You guys probably learned that as I in your math classes. When you put it in your calculator, it'll be I. But in electrical engineering, we use J because I is obviously the thing that we use for currents all the time. And so it would just be wildly confusing. Okay. So if I were to have just a random complex number in the first quadrant of this complex plane, so something like this, I'm going to call this guy right here A. And we could say that the projection of A onto the real axis is lowercase a. And the projection of capital A onto the imaginary axis is lowercase b. Everybody catching what I'm throwing thus far? So so for this rectangular form complex number, we can really just treat this like a two-dimensional or a Cartesian vector, like an XY thing, nothing wild or crazy here. And when we wind up doing mathematical operations with them, specifically like addition and subtraction in a little bit, we'll see that that's the exact same thing as simply adding two vectors together or subtracting a vector from another vector, okay? Now, we can also represent this complex number A in either an exponential form or a polar form, okay? So I'm going to do the exponential form first. I'm going to put it over here on the right-hand side. So in exponential form, we would have our complex number represented by its magnitude, which is just the length of this vector, which I'm representing as the absolute value of that complex number A. And then we would also have some angle, theta A, where I'm measuring my angle from the positive real axis up to my vector. So in exponential form, my complex number A would look like the magnitude of A, e to the j, theta A. Now, your calculators, and I'm going to say this now, fully expecting that half of you aren't paying attention or not synthesizing this information. Your calculators literally cannot do that, okay? Exponential form complex numbers in your calculators does not work, okay? Instead, we typically use a shorthand notation, which is called the polar form, okay? So in the polar form, this is the exact same thing as the exponential form, except that we simply keep the magnitude, we keep the angle, and we throw everything else away. So this same complex number A could be written in polar form as simply the magnitude of A with an angle of theta A. And this form, the polar form, is one of the two forms that your calculator can actually accept and work with, okay? So your calculators can deal with polar form complex numbers, and they can deal with rectangular form complex numbers. So let's talk now about how we could potentially switch back and forth between these two different relationships by hand, okay? So our complex number, as we've drawn it on this complex plane, is just a simple right triangle, right? So if we want to figure out what the length of that vector is, that's just Pythagorean theorem. So we could say that in both exponential form and polar form, the magnitude of our vector A is just going to be the square root of A squared plus B squared, or in more generic terms, it is the square root of the real part of complex number A, quantity squared, plus the imaginary part of complex number A, quantity squared. Okay. Our angle, theta A, again, this is just going to come from simple trig identities, is going to come out to be the arctangent, or tangent to the minus 1, of B over A, which it would be more generally expressed as the inverse tangent of the imaginary part of A divided by the real part of A. So we've now expressed our exponential and polar form magnitude and angle in terms of our rectangular parts for our complex number. So it would be helpful if we could potentially go the other way around, right? So our real part is simply going to be the magnitude times the cosine of that angle, theta A. And the imaginary part is just our magnitude times the sine of that angle, theta A. And so now we've got enough information to go back and forth at will. Now, I will tell you that sometimes your calculator can have hiccups when we're doing this kind of stuff by hand. And I'll explain what I mean by that with an example problem here. Okay. So let's say that I have some complex number x is equal to -5 plus J3. Okay. And my goal is to get X into either a polar form or an exponential form. Okay. So let me just write convert to polar / exponential here. So our magnitude of that complex vector X would simply be the square root of our real part, which is -5 squared, plus our imaginary part, which is 3 squared. And so if my mental math is correct, that is the square root of 34. 25 plus 9 is 34, right? Yeah. This part, perfectly fine, okay? But if we were to calculate our angle, theta x, that would be the inverse tangent of our imaginary part, which is 3, divided by our real part, which is -5. So I want you guys to throw this operation into your calculator for me and confirm that you get the same result that I do. So inverse tangent of 3 divided by -5. I got -30.964 degrees. Other people got that number. Okay. It's wrong. Can anybody tell me why it's wrong? So you're very close to the answer with that comment. Okay. So if we look at that complex number, -5 plus J3, where would that lie in our complex plane? Which quadrant? The second quadrant. That angle of -30.964 degrees, what quadrant does that lie in? The fourth quadrant, okay? So if I were to plot this thing out, so let's say I need to go -5 in the x direction, so let's call that out to here. So this is going to be -5, and then +3 in the y direction. This would be my complex number x as it was defined in rectangular coordinates, right? Well, if we wanted to find x based on these polar coordinates, we would need to go out the square root of 34. So the square root of 34 is probably a little bit larger than 5. Let me just throw it in here real quick and see. 5.8. So we would essentially be somewhere in the ballpark of out here, and then we would need to rotate down by -30.964 degrees. So that would be something looking approximately like this. So as it turns out, these two complex numbers are exactly 180 degrees away from each other, okay? So this angle right here is exactly 180 degrees. The reason why this error occurred is because the inverse tangent operation on your calculator can't tell the difference between a negative sign in the numerator or a negative sign in the denominator. So it's always going to return an angle that is in quadrant 1 or in quadrant 4. It literally can't give you anything in quadrants 2 or 3, okay? So this is a pretty serious limitation of kind of doing this stuff by hand. Luckily for you all, if you picked up the Casio 115 or a Casio 991 or a TI 36X, it can actually do these conversions automatically for you and you will never have to worry about whether you need to remember to add or subtract 180 degrees by doing this stuff by hand. So this is one of the reasons why having a good calculator for this particular portion of the class is so important, okay? You can technically do everything with that peasant TI 30 calculator that some of you had on the first day of class. And you'll spend 4 times as long as everyone else that's just doing it in their other calculators that can do everything automatically, okay? So a lot of what we're going to do today for the in-class assignment is I'm just going to try to teach you guys how to use your calculators because this is so critical. Okay. So for what it's worth, for those of you that have a TI calculator, you can, I was trying to get my license updated for my virtual calculator and it was being a pain in the ass this morning. So I'm just going to have to describe what to do, but it'll be okay. So for those of you with a TI calculator, you could type in -5 plus 3 and then press the pi button 3 times. So pi brings you to the I, the imaginary operator, okay? And if you press then second pi, that brings you into the complex menu, and option 5 converts from a rectangular form complex number, excuse me, option 4 converts from a rectangular form complex number into a polar form complex number. And when I put that in my calculator, I got x is equal to 5.831, which happens to be the square root of 34, with an angle of 149.036 degrees, which is exactly 180 degrees away from that erroneous angle that we talked about. 4. For those of you, how many people have a TI 115, like one of these guys? Or excuse me, not a TI, a Casio 115. Okay. So for the people with the Casio 115s, you would have to press the mode button and then press option 2 to go into complex mode. Then you could type in -5 plus 3 and press the engineering button, ENG. That's where you get your imaginary operator I. And then you could press Shift 2 to bring up your complex menu. And then option 3 converts to polar form. How many of you guys have the Casio 991 that looks like this? Several of you guys, great. For the Casio 991 that looks like this with the white face and or the white bezel and all that kind of stuff, you would press menu and then scroll down to option, oh, let me find it. Oh, it's just 2. Okay, so menu 2, type in -5 plus 3, also just press the engineering button. But for you guys with this particular type of calculator, all of your complex operations are under this option key in the top left-hand corner. So if you press option and you scroll down to the second page, option 1 converts to polar form. I don't have the even newer version of the 991 on me. I haven't bought one of those yet, but I can show you how to use it real quick. So if you have the FX 991 Class Wiz in black like this, I believe first you need to press settings. Maybe you don't. Where's the all clear button? Press, let me double check this. Press home first, and then find the window that says complex and press the EXE button. That's putting your calculator in complex mode. Then you would press -5 plus 3, and then you press the catalog button. And the first option when you're in complex mode is a menu that says complex. And that's where you find your imaginary operator I, your angle operator, and all of those basic complex functions. And then I would press catalog again. There we go. And if you press the format button, that's how you can switch between rectangular coordinates and polar coordinates. I explained that one really poorly because like I said, I don't have one of these, but I will come by and help you guys with this stuff a little bit. You forgot the I button by pressing engineering button gives you your imaginary operator. Everything else is fine. So if you press equal, you got the same metric. Yep. Okay. So let's talk about mathematical operations now. So the first operation that I want to talk about is the complex conjugate operation, and it is the only operation that is strictly for complex numbers that we're going to be dealing with. Okay. So the complex conjugate operation is designated by an asterisk. So if we have some complex number A is equal to lowercase a plus jb in rectangular form, or it's equal to the magnitude of a e to the j theta a in exponential form, or the magnitude of a with an angle of theta a in polar form, a conjugate is simply changing the sign on the imaginary part of this complex number, okay? So that means instead of having a plus jb, we would have a minus jb. That's an asterisk to the upper right. Yeah, that is the asterisk that is denoting you are performing the conjugate operation. Okay, so anytime you see an asterisk like that, that means you're taking the complex conjugate. It is not implying any sort of multiplication. I cannot be, put too much emphasis on that. Asterisks with complex numbers mean conjugate that complex number. So if I were to look up here at the top real quickly, if I flip the sign on my imaginary part so that now I would have a minus jb, what would happen to my angle theta a? So let me put it on the screen here, right? So I'll do a conjugate down here. Okay. So this is a conjugate. The real part is still just lowercase a. The imaginary part in this case is now negative b. So what's going on with this angle? What's that? Well, it's going to be in the different quadrant, but what magnitude will it have for that angle? So it's just essentially, if I change the sign on the imaginary portion, is the exact same thing as changing the sign on the angle, right? The magnitude is going to stay the same because b and negative b have the exact same length. They're just in different directions. A didn't change, so that angle magnitude stays the same, but instead of being in quadrant 1, it's now in quadrant 4, which means it's just negative theta a. So if we go back down here, I could define a conjugate then as the magnitude of a e to the minus j theta a, or the magnitude of a with an angle of negative theta a. Before we move on from this operation, I want to show you guys an interesting identity, okay? Actually, no, I can't do that yet because I haven't explained how to do all of the other mathematical operations. So we'll circle back around to this one in a couple of minutes, okay? So let's talk about addition next. And by the way, I know that I'm going through this relatively quickly. If you guys have any question, please let me know, and I'll be happy to try to explain it better. So let's say that I have complex number A is equal to A plus JB, and complex number B is equal to C plus JD. If I want to perform the mathematical operation of complex number A plus complex number B, I would just have complex number A substituted in here plus complex number B substituted in here. And we're going to treat this exactly like we were just adding two-dimensional vectors together, meaning that our x components add, or the real parts add, so that we would have a resultant of real part of A plus C, and then our imaginary parts are going to add together. So we would have a resultant imaginary part of plus J, B plus D, like so. So anybody have any questions, comments, concerns about that simple addition operation? Okay. It's just the real parts added together plus J, the imaginary parts added together. Okay. There is not an easy or convenient way to do addition by hand with polar form or exponential form complex numbers. Okay. That being said, your calculator doesn't care. So you can totally add polar form complex numbers together all day in your calculator. You just can't do it by hand. Substitution is going to be, or excuse me, not substitution, subtraction, goodness gracious, is going to be very similar. So if I have those same two complex numbers of A plus JB and C plus JD, if I subtract those guys, so A minus B, that's just going to look like A plus JB minus C plus JD. And so the result of that is I'm going to have a real part of A minus C plus J, an imaginary part of B minus D. So I'm just taking the difference of the real part and taking the difference of the imaginary part. So now let's look at multiplication. So multiplication is going to have a way to do it in polar and exponential form. But I'm going to handle rectangular form first, okay? So once again, starting with my basic complex numbers of A is equal to A plus JB, and B is equal to C plus JD. If I want to multiply A times B, so before I write this out, I want to explain something here. If you see two complex numbers next to each other, that is implying multiplication, okay? I will never ever write A cross B because A and B are both vectors, essentially, and I don't want you to confuse that operation with the cross product because that does not exist for complex numbers because it's only a 2D vector. Okay? Nor will I ever write A dot B because I don't want you to confuse that with the dot product, which is another vector operation that does not exist for complex numbers. I can't do A asterisk B because that would make you think that you should be taking the complex conjugate of A and multiplying it by B. So my only option is literally to just put two complex numbers next to each other and pray that you guys remember that that means multiply, okay? So you'll never see A cross B, A dot B, or A asterisk B to mean multiplication because it's too damn ambiguous, okay? So it will always just be one complex number next to another complex number implies multiplication. So here we would have A plus JB multiplied by C plus JD, and we're just going to FOIL this out, 8th grade style, right? So we're going to have A times C plus A times JD plus JBC plus J times J, so J squared BD. So what is J squared? -1. So if J is the square root of -1, then J squared is just -1. So if this guy right here can be replaced by -1, the result of this operation is actually AC minus BD as the real part, plus J, AD plus BC as the imaginary part. Carter, what's up? We shouldn't. That's plus. I'm just having a brain. Oh, no. We are subtracting BD because J squared is -1. Yeah, nope. You had me doubting myself, man. Got to drink more coffee this morning and keep it sharp. Any other questions about this multiplication operation using rectangular form numbers? So this is actually going to be much, much easier if we're using exponential and then by extension polar form complex numbers, okay? So over here on the right, let's say that I had complex number A was equal to, sorry, that should not have the magnitude signs yet. My apologies. So complex number A, e to the j theta A, and complex number B is the magnitude of B, e to the j theta B. So if I multiply these guys together, I'm going to get the magnitude of A, e to the j theta A, multiplied by the magnitude of B, e to the j theta B. And the magnitudes are just going to multiply. So I'll have the magnitude of A times the magnitude of B. And then I will have e to the j theta A plus theta B, right? Because when I multiply two exponentials together, their arguments just add. In polar form, so let me just make a note, exponential. And in polar form, since that's just a shorthand notation for exponential form, that would simply look like the magnitude of A times the magnitude of B with an angle of theta A plus theta B. Any questions, comments, or concerns about the multiplication operation and what it entails in rectangular form or exponential / polar form? We only have 2D vectors, so they're going to come out to be 0. Or at least the cross product will always come out to be 0, but from the way it works. The dot product, I'm not entirely sure, but don't do it. Brielle. Sure. So let's go back to our fundamental definition up here at the top, okay? So our polar form complex number is literally just a shorthand notation for the exponential form complex number, where we keep the magnitude, we keep our phase angle, and we throw everything else away. So if I know that I have a magnitude of, the absolute value of the length of vector A and an angle of theta A, then my polar form complex number is just that length angle theta A. So I was just doing that exact same thing down here, right? Here's my magnitude, and I kept it. Here's my angle, and I kept it, and I just throw the rest away. Any other questions about multiplication? All right, so division using rectangular form complex numbers is interesting to say the least. At least interesting to me. You guys are going to hate it. So if I have that same complex number A is A plus JB in rectangular form, and that same complex number B is equal to C plus JD in rectangular form, then A divided by B would be A plus JB divided by C plus JD. Now, technically, there's nothing wrong with this. However, every other operation that we have done has resulted in a very clear real part and imaginary part in our rectangular form. And we don't have that here. We have a ratio of rectangular complex numbers. So to make this behave like all of the other mathematical operations that we've done, where we have a distinct real part and a distinct imaginary part, we are going to have to get a little bit creative. And that's going to go back to the complex conjugate operation. So let me scroll back up here, and now I can show you that identity. Okay. So let's say that I wanted to do A conjugate times A. And this will be true for any complex number multiplied by its own complex conjugate, right? That would look like A plus JB times A minus JB, which is going to look like A squared plus JBA minus JBA minus J squared B squared. And for what it's worth, this minus J squared is going to look like positive 1. So this would actually result in A squared plus B squared, which is the same thing as just the magnitude of our complex number A squared. So anytime I multiply a complex number by its own complex conjugate, I just get the magnitude of that guy squared. So that's going to be important here when I do this division, because what I'm going to do is I'm going to multiply this by B conjugate over B conjugate. Okay. So that's me multiplying this thing by C minus JD over C minus JD. Now we know that our denominator, based on that identity I just showed you, is just going to wind up as C squared plus D squared. Our numerator is going to look like AC minus JAD plus JBC minus j squared BD. Once again, that minus j squared is the same thing as positive 1. And so we can take this guy one step further. I'll do it down here. And it's actually going to look like AC plus BD over C squared plus D squared plus J BC minus AD over that same denominator, C squared plus D squared. So as I said, division using rectangular form complex numbers is a bit gross. Okay. It's doable, but it's tedious. Yes, Brielle. Absolutely. You guys ready for exponential? Okay. This is way easier for what it's worth. So if I have A is equal to the magnitude of A, e to the j theta A, and B is equal to the magnitude of B, e to the j theta B, then A divided by B is just the magnitude of A, e to the j theta A, over the magnitude of B, e to the j theta B, which results in simply the magnitude of A over the magnitude of B, e to the, positive j, don't know what I'm doing there, theta A minus theta B in exponential. And it's just going to be the magnitude of A over the magnitude of B with an angle of theta A minus theta B in polar form. Okay.